Okay, so hello everyone and welcome to our new session. So today we're going to talk about the clutches and the brakes, specifically for the clutches and the brake design procedure. So I'll try to make these videos as sections. Every section is going to talk about different types of the clutches and the brake. Every section is going to be last for something like 5 to 7 minutes to make it much easier for you to follow up. So our first video is going to be about the plate type clutches or the brakes. So the plate type from the name is going to have two discs that's going to be made on the faces and try to uh, engage or disengage and apply the torque or stop the other part depending on the application we're going to have. There's going to be a brake that's mean one of the shaft is rotating, the other one doesn't. There's going to be a clutch that both are going to be rotating, but the first one is going to be connected to a motion, what we call it, the actuator, and the other one is going to following up the same torque. So the first thing we're going to have a look at is going to be that disc, which is going to be representing the mating phase of the clutches or the brake, the disc clutches or the brake, because both have the same parameters for the design. So we start first with finding the mean radius for the disk face. And this can be done if I know what will be the normal force that applied by the actuating spring, and also the coefficient of friction between the two mating forces, and the torque from the driving shaft. So by collecting these parameters, we can find first the mean radius for the mating faces. It's going to be the torque divided by the coefficient of friction multiplied by the normal force. Torque is going to be in Newton meter. Coefficient of friction is unitless. The N is going to be in Newton, so the answer is going to be in meters. And second, we're going to specify the desired ratio or the R over O and solve for the dimensions. Usually the R over O is going to be anything for the range between 1 to 2.5. In general, we're using the ratio at the beginning to be 1.5, and then we calculate the parameters, find the area, and then we're going to check the W over R ratio, and then we decide if our R over O was large or small, and then we specify another value. So we decide first what will be the ratio between the R O over RI, and then we say that, for example, the RO is 1.5 RI. We can substitute in the equation, calculate for the RI because the RM has been calculated from the previous step. And then by finding the RI and the RI, we can compute the surface area. So the surface area mainly is going to be equal to the area of the outer disk minus the area of the inner disk. Next step is to calculate the frictional power absorbed, and this will be equal to torque multiplied by the omega. Omega is the rotational velocity. Torque is the friction force multiplied by normal force multiplied by the mean radius. The unit is going to be in Newton, of course. Now we go into the next step, which is computing the wear ratio or WR. WR is going to be equal to the absorped power by the cross section, by the face area. So by knowing this value, we will decide if our design was correct or we need to change WR value. So here my WR value is going to be acceptable, otherwise WR is going to be too high. Then we return to step number 2 and we're going to suggest a new ratio for the R over O. And this should be higher in order to get WR to be lower, because the area is going to be, of course, higher. And if the value of WR is going to be too low, then we're going to decrease the ratio to decrease the area, and thus we're going to increase the value for WR. WR for the design usually going to be 0.04 watt over millimeter square for the frequent applications. For WR to be equal to 0.116 watt over millimeter square for the average services. WR is going to be 0.46 watt over millimeter square for the frequently used brakes allowed to be cooled down somewhat between the applications. So tell me something very important. In the equation for the WR, the PF is going to be in watt. The area is going to be in millimeters, not meter. So let's see how we're going to apply this procedure. So first, we need to compute the dimensions of the annual plate type brake to produce a braking torque of 33.9 Newton meters. So now we know that the torque is 33.9. The spring will provide a normal force of 1,423.4 Newton between the friction surfaces. The coefficient of friction is going to be 0.25. The brake will be used in an average industrial services, stopping a load from 78.5 radian per second. So now we have everything. We just need to apply the procedure that we had before. The only thing we're going to have a problem with is going to be suggesting the R over O value. So we start first by compute the required mean radius. Now I know the torque, I know the coefficient of friction, and I know the normal force. So I'm going to put that in my equation. And the answer is going to be 33.9 divided by 0.25 multiplied by 1,423.4. And this will give me that the RM is going to be 95.25 millimeters. We found the mean radius. Now, step number 2, specify the desired ratio of the RO over the RI and solve for the dimensions. So the ratio usually going to be anything between 1.2 to 2.5. Actually, we can practically use 1 to 2.5. So the 1.5 is going to be acceptable value, and we're going to use as 1.5. The equation for the mean radius is equal to the outside radius divided by the inner radius divided by 2. So we said that the RO over the RI is 1.5. That means the RO is equal to 1.5 RI. So I can put that in the equation. And we are going to find that the RM is equal to 1.25 or the RI. Or the RI is going to be equal to 95 that we got earlier, or 92, divided by 1.25. Okay, and we are going to get the value for the inner radius to be 76.2 millimeters, and then the outer radius is going to be 1.5 of this value, or is going to be equal to 114.3. Now with these parameters, I can calculate the friction surface area. And this will be pi multiplied by the RO square minus the RI square. And we are going to use the millimeters, and the area is going to be 0.02278 millimeters, or 22,780 millimeters square. Now calculate the power. I showed that earlier. So the power is going to be torque multiplied by the omega. The torque is given to us already to be 33.970 and multiplied by 78.5, which is the omega. And we get the answer to be 2,661 watt. Now we know the area, 22,780 millimeters square. So we're going to divide the 2,661 by the 22,780, and the answer is going to be equal to 0.116 watt over millimeter square. And for the frequent use, this will be an acceptable ratio for the WR. Okay, so we're going to stop here, and we're going to make a new video for the caliper disc brakes.